Welcome back to the next day in the morning session. We're absolutely delighted to have Raluca, who is giving us a talk now. Raluca is a faculty member at Berkeley. She works in system security and applied cryptography. She has done some really cool, really amazing work, very high impact. She has co-founded multiple startups, which I believe are doing really well. She has a long list of awards, the Grace Hopper Award, a Best Thesis Award at MIT, Sloan Research Award, MIT Technology Reviews 35 under 35.
Wow, you memorized.
And that's so impressive. I was like, if you go Google for her, you like read a lot more really interesting stuff about Raluca. So anyways, I'll give it over to her and we're all excited to hear what you have to say.
Thanks, Shubhangi. Can you hear me well? Okay, great. So yeah, as Shubhangi mentioned, my work is more applied in building secure systems with the help of crypto theory. And I chose this work in particular because the core of this system is, I would say, understandable for a more general theory audience, because I know many of you here don't actually come from a cryptography background. So hopefully it's understandable even without crypto background. So basically in this work, we're trying to address a long-standing issue with Oblivious Storage, the fact that it doesn't scale. And I'll explain what that means, but basically it has been having a scalability bottleneck for more than 20 years since we had the initial protocols. And we managed in this work to basically overcome it and manage to have an Oblivious Storage system that can actually scale. So first question is, why did we call our system Snoopy? So Snoopy stands for Scalable Nodes for Oblivious Object Repository. My student am I slightly embarrassed here, but really the one of the main reason actually is that Emma loves calling her systems Waldo, Dory, Snoopy, and you got the theme. Sorry, Emma, I'm putting you on the spot, so Emma is here. And the other student, Vivian, is an excellent logo designer and graphic designer. So she did this original logo. And you'll see in the talk, all the people and dogs are her original artwork. But more, and if Vivian couldn't be here today because she's in Italy presenting an IEEE Euro SMP, and she won the best paper there, so she's busy. But really, the credit goes to the two of them. They've done the hard work on this paper. All right. So I'm going to very quickly motivate what Oblivious Storage is for those of you who are not familiar. For those of you who know it, I'm going to go pretty fast through it. So you might have heard of end-to-end encryption. Basically, we want to encrypt, let me use this. Want to encrypt the data at a sensitive data at a server, like for example, a medical disease store, such that if an attacker breaks in, they just see encrypted data, right? And today even WhatsApp uses end-to-end encryption, and many of the systems today use end-to-end encryption. And it's called end-to-end because the user is the only one that has the key. Just the ends have the key to decrypt the data. Any intermediaries only have encrypted data. And so you think that this provides, very, very strong security guarantees, but, it's not enough because there's still an amount of information leakage to an attacker watching how the data is accessed. Okay, so the data is encrypted, but seeing the fact that object 1 is fetched versus object 2 versus object 3. And just to give you a very quick example about that is, let's say we all know it's a public knowledge which diseases are more common and kind of their relative occurrence. In particular, COVID is super common today. So an attacker knows this as well. And now an attacker is just going to watch which of these disease rows are being accessed with what frequency. And let's say at the end of, a day, there's this many accesses for each one of them. So just from that frequency, it can infer that object 1 is COVID, object 2 is flu, and object 3 is asthma, right? And now patient Charlie comes to the doctor, and the doctor diagnoses Charlie with COVID, so it accesses the COVID record, which the attacker can see, and infer that Charlie has COVID. Okay, so basically the data was encrypted at all times, but just from which object was accessed, the attacker was able to infer what disease the object has, and then that Charlie has that disease. All right, so there's been a long-standing line of work on so-called Oblivious Storage, which tries to address this problem. The idea is that the accesses made to storage should look either like random. Basically, the trace of accesses should be, cryptographers call it, simulatable from some public knowledge. So you can create the same trace of accesses or indistinguishable from just knowing things like how many requests there are in a trace, but not knowing anything about the data, right? But you can think of this intuitively as the accesses are either looking like completely random, or they're predefined according to a predefined schedule. If you have this many requests, you're going to have this predefined schedule of accessing the data. So your accesses are not going to reveal anything about the data content or the data IDs. Okay, that's what basically Oblivious Storage does. And there's a long line of really amazing work improving different aspects of this technology. But basically, many of these works have two pieces, two components, an ORM client and an ORM server. And the ORM client has a secret. And this ORM client must be in a trusted place. So must be at least somewhere where the attacker cannot see this key. And then the attacker can observe the ORM server, but all the accesses are going to look like, they don't reveal anything about the object ID, random, or in some case, predefined schedule. So for example, when the doctor does a lookup for COVID, what's going to happen is there's going to be an interaction between this ORM client and the ORM server. Accesses to the ORM server look many times random, or as I mentioned, predefined schedule. And then the doctor gets back the file of interest. The attacker has no clue about what was accessed. In fact, even if you access twice COVID, one after the other, it doesn't look like you're accessing the same thing. All right, so but now to actually deploy this setting in the real world, there has been in the recent years, a very common setup among a number of systems. And the setup is to put not just the ORM server in a cloud, but to also put the ORM client in a cloud, but it has to be inside the hardware enclave because it has this secret key that's not supposed to be visible to the attacker. And this is very nice as a setup because first of all, it solves the problem of where do you put the ORM client. In reality, it's not that easy for us to have a trusted party somewhere. In some theory papers, we say, put it at a trusted party, but who's that trusted party, right? Many companies don't have the ability to set up a cluster, have an administrator manage it, all that really hard work. So they end up putting it in the cloud, right? Anyways. But then the other problem that it really helps is that this communication between the client and the server is very fast. It's because it's in the same cloud and it's not in different parts of a wide area network. So this setup has been, has had some success in this way. So we're going to work in the same setup. Okay, so in this work, we don't really care what enclave you're using. So we're not prescribing any enclave. We're enclave agnostic. We're just leveraging some very basic property that most enclaves aim to provide. And that is all the data that comes in and out of the enclave is encrypted and authenticated with a key that's inside the hardware. And the only thing that the attacker sees is basically accesses to memory. So it can actually see the addresses, and those are side channels, and the attacker can actually see those addresses. And we're going to make sure that those accesses are also oblivious. Okay, so again, the abstract model here is that data comes in and out, encrypted from the enclave, and the only thing that the attacker can see is basically, of course, the size, the time when they come in and out, but also what memory address each data is put at or read from. So the access patterns. And there's a ton of enclaves these days. There's more and more improvements and more enclaves. There's a bunch in industry like SGX, CDX, Nitro enclaves. They're available in the public cloud today, and these kind of deployments are happening as we speak. And there's also a number of academic enclaves like MI6, Keystone, Sanctum, Komodo, and many others. And the academic ones tend to be even cleaner, stronger guarantees and whatnot. But in this work, we don't care about what enclave. We're enclave agnostic. Okay, so in terms of the threat model, it's quite standard. The cloud could be compromised by a malicious attacker that can see everything at the cloud and can also modify everything. So in particular, can view all these memory access patterns we talked about that the enclave is making, also network communication in the cloud. If you have multiple machines, how many messages get sent between them. So really it can see everything. But one thing I want to say is that there's already a bunch of work that exists on preventing the attacker from modifying anything and kind of deviating from the protocol inside the enclave, thanks to, there's authenticated data structures the enclaves have and things like this. And then for the storage like ORAM, you can easily have a Merkle tree on top of it. And there's techniques like Ariadne for preventing rollback. So these things exist, so I'm not going to go over them, right? The main thing that we're going to be concerned here is how to make sure that the access patterns to memory and storage are not revealing any sensitive information. Okay, so that's going to be the focus. The rest is kind of, it's been done, it's prior work. Okay, so about the clients, for simplicity in this talk, assume that the clients are trusted, they own the data, they just want to access it without the server attacker learning anything about their accesses. But in our work, we talk about how you can have malicious clients and how you can have access control in the enclave. Okay, any question about the setup before I go into how we solve the scalability problem and things like this? And in terms of security guarantees are going to be quite standard, and I'm not going to go into them, but basically, oh, a question, sorry, yeah.
No, I was just wondering, so do the client, do these clients compute the ORAM physical addresses, or does the enclave compute the?
Oh, good point. So we will, I will show you how it works, how the system actually works. But here's just a threat model, which is we just typically in crypto we just talk about what kind of attacker model we have, and the attacker model you have to keep in mind is that the attacker sees everything at this cloud that comes in and out of the enclave, goes to memory or inside the storage system. It sees all the IDs that are being accessed. That's really just the threat model. And then how it works, I'll tell you later. But the clients are just going to make requests like, get some ID and then gets the result back. So get and put, it's just the storage system. So just get and put. Okay, and the security guarantees are going to be very standard, in the simulation paradigm. I'm not going to go into them, you can look into the paper. Okay, so here's the goal. We want to have a scalable Oblivious storage system. And let me explain what I mean by scalability by taking the example of a regular storage system that just has, data like object ID, object value, unencrypted, no security of any sort. So here you have users issuing many requests. Give me this object ID, gets back the object. Put this object ID, gets, the value gets changed, and so forth. Thousands of them. Now, let's say that this server can process at most 1,000 requests per second. Well, what you do in a regular storage in that case, if you want to go beyond, let's say you have millions of users, right? You want to go to millions of requests per second or whatnot, you're going to add another server. And what you're going to do is you're going to partition the object ID space. So the first object, the first server is going to have object IDs starting with 0, blah, blah. Assume you hash the IDs. So you take the first bit. If it's 0, then you store the objects at this server. And if it's 1, you store the objects at this other server. So now users requesting COVID are going to send a request to the first server, and users requesting, as Mindflow are going to go to the second server. And now if the second server has a throughput of another 1,000 requests per second, it's quite nice because your system can give you 2,000 requests per second. So what was really nice here is that we added more servers and hence the throughput increased. Okay, so scalability means that as you add more resources, your throughput increases. So we would like the same thing to happen with Oblivious Storage, right? So we can, scale out to large number of requests and, have the same thing from a secure system as we have from their insecure system. The problem is that all existing storage systems have scalability bottlenecks. And here's what I mean by it. Let's take the example of tree-based Oblivious storage systems, and many of them have this shape. So basically, the storage of the server is in the shape of a tree. And when the user requests something like COVID, what's going to happen is they're going to actually request a random path in this tree. And it's random so that the attacker doesn't really know what object is actually requested. and somewhere the object will be on this path, and then this path also gets updated. The next time you have asthma, a request is going to fetch another random path in the tree and modify it. And then when you have flu, another one, and so forth. So basically, all the requests went through the root. And the root is a scalability bottleneck. So if you have this node, it's going to be at some server. That server can only process a certain number of requests, but all requests have to go through that server. Some point the server is, is at maximum capacity. It doesn't matter what other servers you add because all requests go through that server, and the server is a scalability bottleneck. Okay, so this kind of structure is the scalability bottleneck. That's why, they couldn't scale beyond what the server can service. Okay. So looking back at the plain text, the reason why it was scaling so well is that we could send different requests to different servers and proceed in parallel. But that also leaks because now the attacker can tell how many requests go to one server versus another, and again, get some sort of frequency information. So again, it's some sort of high-level access pattern, and infer, oh, there's lots of requests going here, probably COVID is here. So then if Charlie goes to, the doctor has COVID and something from here gets access, Charlie has COVID, right? So you still reveal some access pattern. So this is a tension because what made us really scalable in the plaintext space is what leaks access patterns, right? Proceeding in parallel, having requests go to only one place where the object is what makes us be super scalable because we proceed in parallel. But also that is what introduces the leakage. Okay, so it's a tension here. That's why this was a question for a long time. And even I personally thought a lot about this question. How can we reconcile this tension? How can we have requests proceed in parallel, but still have the guarantee of obliviousness, namely that access patterns going to be independent or look independent from the object IDs. Question?
Yeah, sure. So in the previous slide, how do you know, one more before, when you pick a branching path, how do you know if the information is on your branching path?
Yeah, very, very good question. So I didn't go into the details. This is a protocol called Path ORM. And I just kind of told you the high level structure and why there's a scalability bottleneck. But to answer your question, how Path ORM works is there's actually a mapping between object ID, like COVID, and which path it is on. The user would know. And that mapping is also scalability bottleneck because all requests have to go through the node that has that mapping. So that's another scalability bottleneck. Yeah, great question. But you don't need to understand more details about how this scheme works because beyond the fact that it has bottlenecks, because our design will be very different. All right. So is it clear before I go on what's the problem, why we have scalability bottlenecks, and okay, why it's difficult to solve it? It's okay. So then let's discuss about how we actually build an oblivious object storage that has high throughput and scales like a plain text store. So this is to give you a sense of what Snoopy achieves at a high level. We have, let's say if you have 6 enclaves, in Snoopy you get 26,000 operations per second. So this is 6 enclave servers. If you double them, then you're going to get 72,000 operations per second. And the reason is not exactly double. There's a reason for that. And if you add another 6 hardware enclave servers, you get 130K, right? And the reason is not exactly twice, is because actually we need 4 just to even operate our system. And then there's different types of servers and they have different effects on the scaling. But you get the point. The more resources you add, you can keep increasing your throughput with Snoopy. And to compare with 2 state-of-the-art systems in Oblivious Storage, so Bloody, they can process 6,000, almost 7,000 operations per second. And as you add more and more servers, that's it. It stays stuck there. It cannot go on more because it doesn't scale. And another previous system by us, 1,000 operations per second. right? But for us, you add more servers, you get more and more and more and more operations per second. Okay, so how do we do that? How do we do that? So we're going to split the server side into two types of servers, load balancers and suborams. The suborams, they're each actually going to have a data partition, just like in the plain text case. So there's going to be a bunch of objects assigned to one of them, a bunch of objects to another, and a bunch of objects to another. And the way they're going to be assigned is based on a keyed hash. So basically, from the attacker doesn't know what the mapping is of object IDs to partitions. It's going to be based on a keyed hash, and the attacker doesn't know the key. Okay. Now, we're going to have these load balancers. So basically, each client is going to send each request randomly to one of the load balancers, just completely random with not based on the object ID, completely random. And that's a safe thing to do from an Oblivious standpoint, right? Because it's not based on the object ID. But then each load balancer is going to wait for some epoch, let's say a second, and get all the requests it receives in that second, batch them, and then is going to issue requests to the suborams. But
so for each of these things, if you can just store, for example, in the entire duplication of the database, can't you already just assign people randomly to different ones and be able to scale up? What's the problem?
Right, so if you store an entire duplication database, when you do a write to one of the databases, you have to go to the others as well. So then it's again a scalability bottleneck, because you have to end up doing every one of them. So you want to be able to proceed in parallel with both reads and writes.
So for read-only, this is not an interesting question.
For read-only, this is not so interesting. For read-only, yeah. In fact, read-only could use PIR, which is super parallelizable and super scalable. I probably wouldn't even use Oblivious RAM, although there's a work that has read-only Oblivious RAM that scales. But yeah, this is for read and write. This is an actual object storage where you have get and put. Yeah, good question. Okay, so now if I have my load balancers, have this batch of requests and want to send it, to the respective suborams that have those diseases, it's a problem because again, it's going to be some pattern of a leakage, right? Because if I send them based on the object ID, it's going to be a different number here versus here. And again, there's going to be access patterns leaking. So we have to solve that problem. Okay, so here's how we solve the problem. Well, again, a helpful strawman is the following. So assume that each load balancer were to send, I don't know, all the requests to each one of the partitions. That would be secure, right? Because it sends the same number of requests and all requests to each suboram, but that would not be scalable because then again, you're not able to proceed. You're not able to proceed in parallel between these partitions. Okay. So instead, here's a first idea. First idea is we're going to have this load balancer deduplicate the request. So if they all request COVID, it's going to obliviously, we'll see how a protocol for deduplicating and having only one request for COVID. And then it's going to send the same number of requests to each of the partitions, but this number has to be a number that's computed based on public information. It cannot be computed based on how many distinct requests there are, because again, you would be leaking. So it has to be computed based on public information. Okay, so what's public information? Well, public information is the number of requests that even show up at the cloud. That's something that comes outside of the system, just the number of requests. That's a public information. Other public information is how many servers you have, how many partitions, right? The attacker sees this stuff. So based on this, it should be entirely predictable how many requests we send at each partition so that we don't reveal any information through that batch size. And ideally, we want that number to be smaller, much smaller than the total number of requests sent for scalability. Ideally, you'd want it to be, number of requests divided by number of suborams. But if you do that, you might be in a situation where you send more requests to a sub-ORM than that, so you'll have to drop some requests, and that causes, again, leakage. If you drop requests, because maybe the user retries and you see, timing and whatnot. Okay, so the question is, how are we going to set that batch size? And another insight besides the idea of kind of deduplicating this in an oblivious way is to take advantage of the fact that this is a high throughput setting. Again, we use Snoopy only in a situation where you have a ton of requests. If you have rarely requests, existing systems are good enough because they're optimized for latency being low. But if you have a ton of overload, a ton of requests, then you can start realizing that, okay, well, naturally, those ton of requests are mostly going to distribute evenly between the sub-ORMs. So maybe our bound for the batch size doesn't have to be too large. Okay, so here's what we're going to do. We're going to basically have a balls and beans approach, right? If the balls are the requests that come in at the load balancer, and let's just focus on one load balancer right now. You have a lot of requests coming in at the load balancer. Now, these requests have been deduplicated by the load balancer. They're unique. We'll see later how to do that in an oblivious way, but assume they're unique. And there's lots of them. And you have these sub-ORMs that have assigned object IDs randomly based on a keyed hash. Then you can expect that your requests will distribute relatively evenly across the different sub-ORMs. So what you want is you want to set a kind of a public function B that depends on the number of requests and the number of sub-ORMs that will be always larger with overwhelming probability than how many requests will go into each bin, because you don't want to have to drop a ball that causes leakage. But at the same time will be much smaller, ideally, than the number of requests. Okay, and then of course, to fill up all the way till the batch size, you're going to add dummy requests. Okay, just fake requests to the ORM so that it looks like every ORM is receiving B number of requests. These are the dummy requests. And so we modeled this into a balls into beans problem, and we were able to contribute the bound B that is actually quite close to an even distribution of these balls into bins, but at the same time, we were able to prove that with overwhelming probability, basically, it's a negligible probability that there will be an overflow in any one of the bins. So it's a bit of a hairy analysis. I won't go into it, but the point is that you can look into the paper, and we show that if you have, S sub-ORMs for any set of our requests that are distinct and randomly distributed over the sub-ORMs, for security parameter lambda of your choice, then if you set the bound B to be this, the probability that the request will be dropped is negligible in lambda. Okay. So, of course, if the number of requests is going to be quite small, then actually this number will be quite large, and you'll end up having just send the number of requests to each sub-ORM, so it won't be interesting. But if the number of requests is large, actually, this is going towards this exponential term is going towards 1. So you're going to have an even distribution of requests in balls and beans. So you're actually going to have this scalability. Okay, and just to kind of give you some intuition to this formula, just empirical intuition. If the number of requests increases, let's say we have 2 sub-ORMs. This graph shows you 2 sub-ORMs. Then as the number of requests increases, for setting the security parameter to be 128, you're going to have less and less dummies. So this overhead shows you the percentage that are dummy requests, because that's dummy requests is wasted work. And so as the number of requests increases, we're going to have less and less wasted work, right, up to a certain amount. Now, if you have more sub-ORMs, you're going to have percentage-wise more wasted work, right? Because you have to pad all those sub-ORMs intuitively. And then another graph here is like as the number of sub-ORM increases, then you are able to have more capacity for real requests, right? Because you have more sub-ORMs. Anyways, you can play with this bound and you can look at our paper. And we think that this bound in general is very useful because maybe in other settings as well would be applicable, because it only depends basically on the security parameter here. So the probability of a ball being dropped is depending only on the security parameter. And does not depend, for example, I mean, it depends exponentially on the security parameter and does not depend, it's not like a polynomial dependency. It's an actual exponential, negligible probability. Okay, so now let's focus on, great. So what are we doing at each load balancer? We know the batch size, but okay, how are we actually implementing obliviously this kind of deduplication and distribution of requests at each load balancer? Okay, so remember that we don't want to reveal access patterns in that process. Okay, so here's what we want to do. This is the task. We have a load balancer. Let's focus on one. We know the batch size from that previous analysis. Okay. And what we want to do is we get a lot of requests from users. We want to deduplicate, so remove duplicates. Okay. We don't want to do this obliviously. Okay. Again, the attacker sees all our accesses to memory. So you can't just go, I'll show you in a moment what we can do. But then we want to also distribute them per sub-ORM based on the kid hash function, and then get the requests back and match them back to the original, requests and send them to the user. So I'm going to tell you two building blocks, and then we're going to build this load balancer algorithm from these two building blocks. So we're using an oblivious sort algorithm, which basically takes some values and can sort them in an oblivious way. So this is a building block we're using. For example, in this case, we're using the Batcher network. And this comes with a proof that, if you make accesses according to this algorithm, the attacker cannot tell anything about, which item went where, which object went where. Okay, it's an oblivious sort. Now, we're also going to use an oblivious compaction, where basically we have some items and we want to keep, delete, delete, keep, delete. Okay. So this oblivious compaction algorithm, it's more efficient than, because you could obviously do this with an oblivious sort, but it's more efficient, is going to basically sort them based on what you keep and what you don't keep. And you can actually easily discard these two as long as the amount that you keep is a number that's known by the attacker, like public, based on public information. Okay. So basically we have these two building blocks. They're simple. One, we can sort obliviously, and one is we can compact obliviously. So now let's try to together figure out what the load balancer has to do. Okay, so here's what, these are a number of set of requests that are coming in at the load balancer. As you can see, there's like a duplicate. There's a duplicate, the first and the last, and then there's a few other distinct ones. And so we're going to do a first pass when we're going to assign basically what, just going to do one scan, we're going to assign based on the key hash to which sub-ORM is supposed to go. And assume we have two sub-ORMs, okay? So first one is supposed to go to the first sub-ORM, second to the second, first. So I want to hear, thoughts from you, but just to tell you a little bit more, again, what we want to do is we want to send the ones that are assigned to one to the first sub-ORM and the ones that are assigned to the second sub-ORM, and we want to remove this duplicate. And we want to do this obliviously. So we cannot make accesses of the sort, oh, this is one, I'm going to send it to the first sub-ORM. Oh, this is two, I'm going to send it to second sub-ORM. Oh, this goes to the first, because the attacker can see our accesses, can see we took the first object, send it to the first sub-ORM, the second goes to the second, the third goes to the first. So again, it's going to see our access and infer, information about our object IDs. So the access has to be either kind of random looking, or it has to be according to a predefined schedule. So any ideas what we could do? So we have an oblivious sort, ability to sort obliviously, and the ability to basically compact obliviously. So kind of discard some elements based on a filter. Any ideas what we could do? Yeah.
I guess you can add a bunch of dummies so that you don't reveal that there's only one thing that's labeled 2, and then you sort it. No, you type compact to move all the ones and the 2s and whatnot, and then you sort within each.
Yeah. Exactly. So first, we're going to add a bunch of dummies. How many dummies are we going to add? Again, it has to be a predefined number. based on public information. It cannot be based on what objects IDs we actually have. So let's say that each suborem can takes B. The B is 3. Okay. Then we add 3 dummies for the first suborem and 3 dummies for the second suborem. Again, B is known by the attacker. So what we did here is completely as expected by the attacker. Okay. Now, exactly as what's your name? Surya? Surya. Surya.
Yeah.
Okay. Thank you, Surya. So exactly as Surya said, we're now going to sort this. The reason we're going to sort them is because we want to group together all the items that go to the first suborem and the items that go to the second suborem. Okay, so we're going to obliviously sort them, and now they're nicely grouped together. So now we want to get rid of duplicates, right? So what are we going to do to get rid of duplicates? Again, without the attacker, because we can't go and say, oh, keep this and then cut this one, delete it and then keep and keep. The attacker will figure out, oh, this whatever was the first object, it's kind of duplicated, right? Has 2 occurrences. Any thoughts what we could do to get rid of the duplicates and then also kind of prepare our batches for the different ORMs? Yeah, Amy?
Do the compaction and keep enough W's so both the groups are the same.
Right, exactly, yeah. So basically, first we're going to do a scan to kind of figure out what to keep and what not to keep. So we're going to do one scan. Again, scans are oblivious because you just scan things, nothing based on ID. So we're going to see this and say, oh, object 34, okay, we keep it in mind, we scan the next time, oh, it's a repeat, so no, this will not be kept. But again, this bit here, it's encrypted, the attacker cannot tell what it is, we haven't removed anything yet. And then this one, keep, and then we realize, okay, there's been enough ones, there's been 3 ones, and we only want to send 3 to a suborem. So we're going to say remove. But again, we keep them, we just mark them as removed. And then the same thing for 2, okay, keep, then, oh, we need to keep 2 more dummies because we need to get to 3 and then remove, okay? And now we just do an oblivious compaction, which is basically going to sort out the ones to keep at top and the ones to not keep at the bottom. It's okay to get rid of the ones not to keep. Why? Because the attacker knows exactly how many things we're going to get rid of. Why? Because we're going to send B items to each suborem. So the attacker knows exactly how many we're going to get rid of. Okay? And now it's simple. You take the first 3, send them to the first suborem, the second 3, send them to the second suborem, and you can do that because the attacker expects you to do that. Expects to take the first ones and the first suborem, second, and so forth, right? So you see why all of this has been done in a way that the attacker has no clue how many items were duplicates, how many items went to the first suborem or the second suborem. And at the same time, we're only sending to each suborem much less than the number of requests. So they can actually proceed in parallel and compute in parallel, which is key to scalability, because you can add more and more suborems and have more throughput. And then, okay, so once the suborems reply with the object content, you have to match it back to those requests. Some requests will be duplicated. There's some work you have to do, but that's in the paper. Okay, it's kind of the reverse of what we've done. And I'm not going to go through that. Okay, so the last piece, so you saw how the load balancers work. Now let's focus on what happens to the suborems.
Question.
No question.
Yeah, I have a question. So in the boson-based analysis, it seems that it assumes the queries are distributed uniformly to each of them, but it doesn't seem to be the case in the algorithm you showed. So, for example, if there are 3 points and 2 of them always access the first one, and it's like specific. So how do they do
It's
that?
a very good question, very good question. So actually what happens is that the object IDs are assigned randomly to each suborem. And the requests are going to be deduplicated when they're sent out to the suborem. So you're only going to have distinct requests. So for example, if we go back, this clicker doesn't work. But yeah, that's a good question. That's kind of key. Let me just go really quickly through this. So these are going to be the requests that we end up sending. So we're going to be all deduplicated. So it's going to be only unique values. But now, yes, the requests are not random because the users made them. But the assignment of objects to suborams is according to a keyed hash that's random and unknown to the attacker. So they are random. Yeah, great question. Yeah.
So if all the objects were the same, right, if they were all like 34, then the attacker would say you only send one request to each server, right? Because
good question. So actually, if there were only 34, this would be dummy and dummy. You still send 3.
oh, you still send 3. Okay.
Yeah, you still send 3 because you only send this batch size B, and B depends only on the number of requests that show up and not on whether they're duplicates or distinct. Yeah, so you always still send that B. Now B depends only on how many requests you have that arrive, but not whether they're duplicate or not. Yeah, great question. Okay, so now let's do, let's see how the last piece of the system works, the suboram. And already, if you were to just use a regular ORAM, you are able to proceed in parallel. So you already solved the scalability bottleneck. But here we're actually going to propose a different ORAM than one that exists, because in this setting we can actually do much more efficiently than what exists. Why? Well, because we existing work prioritizes latency, not throughput. But in this setting, we have a lot of requests that are coming in. So we have a batch at each suboram. We have a batch of requests that we have to service at the same time. So let's take advantage of the fact that there's a batch of values instead of just one at a time. And let's take advantage of the fact that these are distinct requests. Okay, so at each suboram, we get a batch of distinct requests. And this is something that we can definitely leverage with Oblivious Storage. Why? Because what's typically hard in Oblivious algorithms is when values repeat, because that's when frequency leaks intuitively. And a lot of what the ORAM work does is to kind of prevent that observation that something repeated. So now if we have a large batch of requests that are distinct, it sounds like we can do way better than the regular ORAM, and we can. So actually, it turns out that Signal has an algorithm that is kind of intuitively going in the direction of what we want. How many of you use Signal? So it's great. A lot of you use Signal. Yeah, great. So I know if you knew, but basically what Signal does when you join Signal, when you have a new contact, what it does is it wants to do an intersection, obviously, with the Signal user. So these are Signal users at the server, and these are your contacts. And Signal wants to figure out who is common, so they can tell you your friend is on Signal. And if you get those annoying notifications, this person, your friend is on Signal, I hate them. But this is what's happening. So they do it's a set intersection, right, of the contacts and the Signal list. But the way they do it is they actually do it with enclaves and Oblivious computation in the cloud. So basically what happens, they take the contacts, they don't want to go for every contact and look it up because it's too slow to do that ORAM for that. So instead, they're taking advantage of the fact that there's maybe thousands of contacts and they're distinct, right? Your contact list is distinct. So it's similar to kind of what we want, right? So what they do is they're going to put in an Oblivious hash table these contacts, and then they're going to do one scan through all the Signal users. And in that scan, is going to look it up in the hash table, see if it shows up or not. And so with one scan through all the Signal users is going to figure out whether all these C contacts are there or not in one scan. Okay, so it's like a batch processing here. And this is much more efficient in realistic terms than doing ORAM, which ORAM is, has fully logarithmic overhead for every request. And this is going to be, linear divided by C, but still in real terms, it's far more efficient than doing the ORAM because of the constants of the ORAM. Okay, so this is what they do. And this sounds, okay, what we want, because the contacts in Signal can be our requests. And this list of Signal users is the list of objects of the suboram. Okay, so now our suboram can do what Signal is doing for a batch of requests and be much, much more efficient than doing a regular Oblivious RAM like path ORAM for every one of these requests. But there's actually two problems. one problem is that their hash table is still kind of slow when you have, hundreds of thousands, tens of thousands of requests, because they were fine with C² for a user's context, but we're having even more requests than that in our system. But the other problem is also that we actually found a security issue in their protocol, in that basically what happens is they have buckets in this Oblivious hash table that they didn't size accordingly, and you have overflow over those buckets. And when you do that, you basically have leakage. So basically what you could do is you could say, okay, so you have these buckets and you can size the buckets based on how many objects map there, which is similar to what happens in Signal when you have an overflow. But that's leakage, because if some object hashed to a big bucket, it's more likely to be requested than not, right? To be in the contact list than not. So because you get this overflow of buckets in Signal, there's actually leakage and they're not fully oblivious. Okay, so we instead want to have a bucket size that is fixed always, and you don't get overflow. This sounds familiar. It's again the problem we had at the load balancer showing up here at the sub-ORM. So we could actually use our bucket, our way of choosing the batch size for this scenario as well. But it actually turns out that the buckets would be a little bit large. It works, it's oblivious and secure, but it actually turns out that the buckets are a little bit large, and we can actually do something better, something easier, something faster, is we can use a data structure by Chan et al., an oblivious to tier hash table, which makes sure that the overflow buckets are put in a second hash table, and that will result in smaller buckets. And I'm not going to go into this result, you can go and read it, but intuitively, because you have a second tier, second level of the hash table, you for the overflow, you're able to get much smaller buckets. And so this is going to be result in a much smaller, much more efficient scan through each bucket, because the buckets are going to be smaller. And actually, we talked to Signal people about this, and we told them about the security issue and about how to solve it. And so they were anyways in the process of revamping their protocol. So hopefully they will include our ideas, but they're aware of the security issue. Okay, so right. So basically, this gave you a high level of how Snoopy works in the time that I had. And so I told you of how you have oblivious deduplication and distribution of the batches at the load balancers, how we chose this batch size to be basically based on public information in using this balls and beans analysis that you can see more about in the paper. And that's smaller than sending all requests at one sub-ORM, so that really gives you the ability to parallelize and be efficient. And then I told you how we have basically the sub-ORM design inspired from the Signal protocol, but using a two-tier hash table instead. And you can see more details of that in the paper. And the final bit that you can see in the paper, and I just mentioned the high level, is we have a planner. Why? Well, figuring out, okay, I have 1 million requests per second, figuring out how many load balancers versus how many sub-ORMs to have, it's an optimization problem. And so we have a planner that basically outputs a system configuration. You tell the planner, I want to service this many requests per second, and some upper bound in your latency, and it can compute how many sub-ORMs and how many load balancers you need to optimally achieve that. And of course, we have formal security and linearizability proofs for consistency and for security. Yeah, question?
Yeah, so the planner, is this something that you would just do once at the beginning, or could you create a system that has some load balancers and some ORM, and then later say okay, now I want to add one or the other and change that dynamically?
Oh, that's interesting. It's interesting. Yeah, in our case, you do it at the beginning, but it's actually, your name is Alita? Yeah, okay. It's a very good question, and I think it could be interesting next step to look into how to dynamically adjust while being oblivious, right? Because you don't want to just say, okay, I'm adding another subordinate, give me this piece, and you want to do it in a careful way. But right now we're just having it at the beginning. The nice thing about the load balancers, those are the easiest. You can just throw in a new one. Just add a new one. Why? Because the load balancers are completely independent of each other. They don't have state. You just get a bunch of requests. They, compute the batch size based on number of requests and distribute obliviously those requests. And then after that, you don't keep anything in mind. So you can spin them up and down very easily. The suborm, you want to be a bit more careful in when you add a suborm distribute the workload. Yeah, shouldn't be too difficult. Yeah.
I guess if multiple people try to write to the same index, then an arbitrary one wins. I guess.
Yes, absolutely. So we have guarantees on I didn't go into linearizability, and basically what happens is the load balancer can choose the order of the request that it gets, and it can choose which put wins. Yeah, and a lot of these scalable object stores, even for plain text, don't have very strong, have this kind of consistency guarantees anyways. Yeah, good question. Yeah.
They happen in the server or like across the server?
The rebuilds that Lalit asked about?
No, like the rebuilds when like ORAM has like rebuild the entire table, right, after some queries. So
Good point. Yeah. So basically the suborm is the one that's kind of like an ORAM for a partition. And the suborm is the one that's going to basically, whenever you have a put, is going to update that value. And yes, there's a shuffle going with every scan. There's a shuffle happening that will, oblivious sorts that will basically update the value that gets put. Yes, with every batch of queries, it happens, absolutely. And as I mentioned, the reason is that we have so many requests, so many queries, that in one basically linear scan and oblivious sort, we're able to update and service the requests. And we prefer the complexity to be linear than to be logarithmic times the number of requests, because there's so many requests and the constants of path ORAM or the tree-like structures are high. So this is much more efficient to kind of do a scan and an oblivious sort for that many requests.
So if you need the content on the ground, otherwise you won't have that much storage. You can't expect a user to have that much storage because the batches are huge, and then like
yeah. Honestly, there's all these works that say, oh, you can have the ORAM client in some trusted place. Where's that trusted place? Who gives it to you? Thinking of pragmatics, as a systems builder, having companies. Where is it? Where is it going to go? Who's going to run that for you? Especially when you have many users. People are going to put it on the cloud. Well, if you put it on the cloud and you trust the cloud, might as well run your whole storage there, right? So yeah, it would be an enclave in the cloud, yeah. And you only need to have in the enclave the pieces that handle the key and the compare and swap and things like this. You don't need to have in the enclave the actual storage that can be outside the enclave and fetched in and out of the enclave as you need it. Great questions. Okay, so really quickly, I'm just going to go through the evaluation. So Snoopy is open source. And you can find our implementation here. And also this was published at the security conference, SOSP, systems conference, SOSP. And the nice thing that SOSP has is optionally, they can evaluate your open source artifact. And they basically give you badges if they manage to make sure that it's functional, has all the functionality you promised, and also the results were reproduced. So we got those badges. Basically, the reviewers were able to reproduce our results based on open source and check the functionality of our system. So feel free to use it, build on it, improve it, and whatnot. Give us feedback. Okay, so in terms of evaluation, I'm just going to show you an evaluation on 18 machines on Azure. Azure has enclaves, which is great. And I'm going to compare to two state-of-the-art systems, Obladi and Oblix, which have the scalability bottleneck. So you can see that as you add more machines, Obladi and Oblix just stay put at the throughput because they, at this throughput, they've basically filled up to capacity their server, their bottleneck server, and are unable to scale. But with Snoopy, let's say you batch for 1 second. So you batch for 1 second. You can have, as you add more machines, you have an increase in throughput. If you batch for half a second, then you have still an increase in throughput, but the throughput is going to be less, right? Because for more requests you have, the more balancing we're able to do between the sub-ORAMs, the less dummies we're going to have, the more efficient our sub-ORAM protocol will be, and so forth. But of course, you can't choose this batch epoch, I mean, the epoch while you batch to be too large, because that affects your latency, right? You have to wait for that much when you send a request to get, all those requests in a second, you have to wait for a second. So the more latency you're able to tolerate, the more throughput we can give you, because you can batch more requests. Okay, so to conclude, Snoopy is an Oblivious object store that scales like a plain text storage. That kind of curve is what you want to see, what you see in a plain text storage, and what you now get to see also in our Oblivious storage system. And yeah, you can read more in our paper, or you can look at our open source. And yeah, thank you. I'm happy to take more questions. Yeah. Interesting open question in the space. I would say there's many. I would say figure out the way that you don't increase the latency, but have the throughput scaling, but without having to increase latency that much. Because right now, if you take path ORAM and existing ORAM system, they have better latency than Snoopy has for a low throughput scenario, right? Where you just get a request here and there. They're much more efficient than us. We are efficient more than a ton of requests, and we just want to scale and scale and scale. So it'd be nice to see if one can have both low latency and high throughput. So taking Snoopy and like low latency. I think that would be very, very interesting.
What is the asymptotic overhead? Is it log squared for that?
So the sub-ORAMs, it's actually linear because you scan the sub-ORAM for the batch size. So it's linear divided by the number of requests. And actually in the ORAM and PIR literature in the past few years, there's been a number of works that are saying, forget about the polylogarithmic, like path ORAM, go for linear because it's more efficient, because the constants matter, and the constants are very large with ORAM compared to just a quick scan and servicing multiple requests.
So you're basically going to look at every, like all the contents.
In the sub-ORAM, yes, exactly. But if you do want to have polylogarithmic overhead and still scale, you can still use our load balancer algorithms and our batch size selection, but have a regular ORAM polylogarithmic at the sub-ORAMs. And then you have polylogarithmic overhead, and you still have the throughput scaling. You still don't have the bottleneck. This kind of our sub-ORAM design is kind of an addition, because we noticed that if you have lots of requests in there, this thing can do something much more efficient in terms of concrete costs. But it's not the linear. Again, you can have polylogarithmic and no scalability bottleneck. They're not intentional or anything, not in conflict. Yeah.
So when you're making like the same number of requests to each of the sub-ORAMs, it can kind of fundamentally leak that ORAM is being used. Would it adapt, do you think, to any sort of arbitrary distribution, right? If you wanted to like add in like not sick one and sort of skew the distribution to make it look like you have more requests like this, would that adapt to a system like this, or would that kind of introduce more challenges than it's worth?
So I don't know if I understood the question well, but I think the question is, if the distribution is really skewed, you have a ton of some disease and less of another, then whether this would be secure, would have to change, adapt. The system won't adapt to that. So we are oblivious, which means that no matter how skewed the distribution is, the same behavior happens.
She's asking if you want to hide that you were trying to hide. Did you hide that you were using an ORAM?
Oh, to hide it, I'm even using ORAM.
Right. Yeah.
I see. I mean, in principle, you could hide that you're using ORAM, right, by having some sort of generic system, right, a universal circuit style thing, that is just doing much more requests, right? You define a unit of an operation that does, I don't know, touch a certain amount of data, does a certain amount of reading, and to that unit of operations, you can probably implement something like this or like ORAM, probably very, very slow. But in principle, yeah, you can. The other thing that you might want to hide is how many requests arrive at the cloud. So then the secure messaging literature has situations where you just use it constantly sending requests, and obviously becomes very slow.
So I feel like I'm not understanding something. So let's say like there are many servers with like people want to write at requests, but like everyone wants read requests to like a particular subforum. Does that mean the number of dummy added is like linear in terms of the number of subforum?
That's a good question. So the question is, let's say everybody requests the same disease, and we discussed this example in the beginning. And so then will this massive number of requests all go to one subforum, and then you have to add dummies to the others? The answer is no, because the whole like crucial actually insight of our work was to duplicate these requests. So when they show up with the load balancer, we basically deduplicate. There's the same disease request in much times. We only make one request to one subforum. When we get the response back, we multiplex it as a response to all these requests. And that was really, I would say, a really crucial insight that enabled us to do this work and have scalability. Yeah, exactly. Otherwise, you would run into that problem of having a ton of requests at each subforum. Absolutely, yeah. Okay, so I think I'm running over time, but I'm also happy to chat.
Last question. Time for one.
Had great questions, really appreciated and involved. Yeah, Tanya.
There's some same direction with speed request, I understand how the duplication works. Write request just said, then the other one bounces. I mean, one gets through.
Yeah.
But if you have everybody write the same, like you having put your aggregation, the batching period for too long, and everybody is like, this is the favorite thing to write to. Wouldn't you just like totally linearize this and make it super slow? Also, wouldn't that leak information on how often you actually have the same access?
Yes, good point. So each load balancer is going to wait for requests for a certain amount of time, right? And can decide which put wins among the requests. And then what happens is that the subforums are giving the small chunk working chunks in epochs. And each epoch is for one load balancer. Then the next epoch is for the other load balancer. Next epoch for the other load balancer, and so forth.
Okay, so it's only a problem if two arrive at the same load balancer.
Yeah, exactly. If two arrive at the same load balancer, one is going to be overwritten. Yeah, absolutely.